Why would generations of scientists spend decades trying to measure the Earth's bumpy shape? Published on 8th of June 2026, the piece moves past the technical difficulty of measuring the globe to find the philosophical reason for doing it at all. The history of geodesy suggests that precision functions as a necessary friction for the scientific mind, moving beyond simple accuracy. By chasing tiny discrepancies in the Earth's curvature, researchers were forced to abandon old assumptions and stumble upon the internal dynamics of the planet. Measurement is framed here as a discipline of humility, showing how the physical world eventually corrects the most elegant theories. Written by Miguel Onosource in Aeon, narrated for Ava. Sometime in 1852, the Swedish astronomer Nils Haqvin Selander travelled northward past the Arctic Circle to oversee the completion of one of the largest projects in precision measurement in human history. Over the previous 40 years, he and his predecessors, most notably Friedrich Wilhelm von Struve, had been occupied by a seemingly simple problem in physical geodesy. What is the shape of the Earth? By the 1850s, scientists knew that Earth is not a sphere, and its surface flattens closer to the poles. Selander wanted to find out by how much. To do so, he measured the length of several sections along an arc of meridian, a line of longitude, stretching from the Black Sea to the Arctic Sea. The arc covered more than 20 degrees in latitude, or, by their estimate, 2,821.833 kilometres. It required a mind-boggling amount of work. To measure such a long distance exactly, the meridian was split up into 258 interconnected triangles, whose internal angles were measured repeatedly by sending light signals and recording them with small telescopes mounted on so-called theodolites. In each measurement, they needed to know their exact altitude over sea level, based on a large network of continuous measurements with spirit levels and barometers. 10 sides of their triangles had to be measured by manually concatenating standardized rods hundreds of times using specialized apparatus. I won't even start listing all the calculations and statistical exercises involved in aggregating all that data. And Selander and Struve were not alone. Over the course of the 19th century, similar measurements would be completed in most of Central and Western Europe, North America, Great Britain, Japan, and British India. Why would anyone invest so much effort into measuring Earth's shape? There were many economic and political incentives for constructing precise maps, but this cannot be the entire story. Geodesy wasn't the first time scientists had sought extremely precise measurements of apparently obscure details of the world, nor would it be the last. Think, for example, of measurements of the magnetic muons in the Large Hadron Collider, or astronomical measurements of the precise angular momentum of our galaxy. What justifies the enormous value scientists attribute to pursuing precise quantitative measurement? The quest to measure Earth's shape offers an exemplar that helps us understand why precise measurement is valuable. That value is not exhausted by the economic value of precise data. Neither is measurement's value merely instrumental, a tool for confirming our scientific theories. Measuring matters for deeper reasons than are immediately apparent. Before we turn to the story of Earth's shape, a few words on what quantitative measurement is. We hear about quantities all the time, in science journals, political debates, educational assessment, and wellness apps. Despite being so familiar with quantitative concepts, we rarely ask what exactly we mean by them. It's commonly known what sustainability scores, global warming targets, or earthquake magnitudes are, but the incremental differences on each of these scales are less understood. These incremental differences, however, are the defining features of quantities. Most people could tell the difference between a minor tremor and city-destroying quake, but what about a magnitude 7.0 and 7.2? What properties of earthquakes do such differences correspond to? To play such a strange language game, we need to make sure we know its rules. More precisely, any useful quantity needs rules of measurement. In an homage to one early device used as a rule of measurement, we tend to refer to such rules as scales. Scales spell out how to assign magnitudes to objects. As a first approximation,
it is helpful to think of measurement simply as the art of building scales. Scales can be physical devices, like a fulcrum balance or a thermometer, from which we read off magnitudes. They can also be cognitive devices, such as the scales for measuring reading comprehension. Such scales take your answers to specific questions about a text and compute a reading comprehension score with the help of statistical regression and some ideas about what usually makes texts difficult to read, the number of words, their familiarity, etc. Usually, scales are a mix of both, a physical device and many cognitive devices that we use to correct, read, and calibrate it. Models, theories, rules of thumb, etc. So much for quantitative concepts and the careful art of measurement that makes them meaningful. But why go through the ordeal of building scales? Why measure at all? Modern science teaches us that building good scales can take centuries, involve many hiccups, and require hard physical and intellectual labour. It is perfectly legitimate to ask why measurement is worth that effort. History vindicates the importance of asking that question. For a long time, it was far from obvious whether quantitative measurement should be central to science. First, because it is not obvious that quantitative concepts are always the right concepts to use, and second, because it is not obvious that precise measurements of quantities are feasible or even desirable.
Here is the first challenge to quantitative measurement. Should we be using quantitative concepts instead of qualitative concepts at all? The history of philosophy and science is full of arguments to the contrary, which are far more cogent than the modern reader might suspect. From Aristotle to the early modern period, it was widely assumed that many phenomena could not be quantified. The label quantity was reserved for those attributes that are extended in space and time, which excluded attributes like density, temperature, or electric charge, let alone reading comprehension or economic growth. Galileo evidently considered departures from the constant period a minor, inevitable result of nature's complexity. Here is the second challenge to quantitative measurement. Why should we expect that the world is well behaved enough to provide us with precisely agreeing measurements of the values of quantities? Let's forget about the first challenge and assume that all features of the external world are quantifiable in theory. Even staunch believers in quantities, like René Descartes, I know of no material substance other than what geometers call quantity, and Galileo Galilei, this grand book, the universe, is written in the language of mathematics, were by no means champions of precision measurement. Instead, they thought that experiments or measurements might at best demonstrate our quantitative theories only roughly. The messy world of experience, full of friction, resistance, and asymmetric bodies, is so complex that it prevents any such agreement from being very precise. Pursuing precision in nature, outside the exact world of mathematics, is futile. Here is a fun illustration.
When Galileo used a water clock to measure the constant periods of small arc pendulums, swinging back and forth across roughly 10 degrees, he concluded that he demonstrated that all pendulums preserve their constant period, whatever the size of their arc. It takes only a few seconds of playing with a large arc pendulum, more than 30 degrees, to prove him wrong. A fun experiment I like to do with my students. For large arc pendulums, the period depends on the swing's angle, which makes them less accurate for timekeeping. In all his work on pendulums, Galileo must have encountered this phenomenon, yet he evidently didn't consider departures from the constant period to be either interesting or troublesome, but a minor, inevitable result of nature's complexity. Let's take stock and return to our initial question. Quantitative concepts differ from all other concepts. They require measurement scales to be used appropriately. Measurement is exceedingly difficult, and it is not at all obvious how important measurement is to science. Why then do we measure? With almost 400 years of additional experience in measuring, I think we owe Aristotle, Galileo, and Descartes an answer. If measurement has helped us do better science since then, we should be able to tell why it made science better. Here is my answer, in brief.
Quantitative measurement is neither warranted because all phenomena, deep down, have a quantitative structure, though they might, nor because we will always succeed in achieving increasingly precise and convergent measurements. Rather, measurement, if taken seriously, imposes tight constraints on our theoretical and mathematical imagination that push it in the right, productive directions.
Measurement forces us to learn more about that world than we would otherwise. Constraint here has a double meaning. First, measurement can constrain how we develop theories. A good quantitative theory needs to spell out rules of measurement, i.e., they must contain quantities that can be related to observable phenomena. Isaac Newton revolutionized celestial mechanics, for example, by not just talking idly about forces, an entirely theoretical concept at the time, but by proposing exact rules for measuring the magnitude of forces from the motions of planets, pendulums, or projectiles. Second, measurement can constrain how we revise our theories. As we teach in philosophy of science intro classes, our imagination is limitless, but our data is scarce. Why cling to some theories that explain the data, but not others that may do so too? Part of the answer is measurement. Only some theories have a track record of continuously improving themselves to predict more phenomena that can be measured. The moral is this: measurement forces us to learn more about that world than we would otherwise. To measure what we are talking about, we build better instruments, we run more powerful statistical calculations, and we model an increasing number of causes that may affect the instruments. Much of our best empirical knowledge comes from these strenuous exercises. A measure worthy of its name is the result of years, decades, or centuries of repeated testing and improvement, and a measurable quantity emerging from such a process rightly enjoys a special degree of trustworthiness. So much for the short answer. To actually grasp its moral, let us return to our example, the effort to measure Earth's shape. When Selander in 1852 was measuring the arc of the meridian from the Black Sea to the Arctic Sea, he was trying to determine the ellipticity of the planet. The idea is simple. The more flattened the Earth is at its poles, the more curved its surface is at higher latitudes. Measurements of Earth's ellipticity long predate 1852, and they continue today with the help of artificial satellites. They are great examples to understand the long-run value of precision measurement, if there ever was one. Measurements of Earth's ellipticity first became a prestigious problem because they promised to settle a debate between skeptics and proponents of Newton's theory of gravitation, developed in his Principia, 1687. Newton offered a range of empirical arguments for his universal law of gravitation, Fg proportional to mm over r squared, where the gravitational force, Fg, is proportional to two masses, m and m, over the square of r, the distance separating them. The numerator of that law, the product of m and m, is supposed to refer to any masses whatsoever, not just the masses of planets that show up in astronomical calculations. Nowadays, the universal scope of the law is understood as a well-tested and defining feature, but to many of Newton's contemporary readers, it was merely a risky generalization beyond the available data. Even Newton's own editor, Roger Coates, found it hard to accept. If Newton was right, the masses inside the planet would also affect its shape. By Newton's own standards, evidence for this generalization required, at the very least, successfully predicting a measurement of bodies with more ordinary sizes and masses, not just celestial ones. As the Principia was being printed for publication, Newton finally realized that there was at least one accessible, mathematically tractable, and measurable quantity that fit that bill: Earth's ellipticity. Earth's ellipticity is caused by its rotation, but if Newton was right, the masses inside the planet would also affect its shape, depending on the manner in which they attract one another. He predicted that Earth's diameter at the equator is 1/230 longer than its polar axis. If Earth's internal parts do not attract each other and gravitate only towards its centre, as Newton's critics believed, it would have a smaller ellipticity of about 1/578. Furthermore, the variation in gravity measured on Earth's elliptical surface, however oblate, will be much stronger if Newton's theory is correct.
And so, over the next 100 years or so, many brilliant minds, from Pierre-Louis Maupertuis to Émilie du Châtelet and Pierre-Simon Laplace, tried to establish whether measurements of Earth's ellipticity and surface gravity supported Newton's law. By the time Laplace had completed the first volumes of his Traité de mécanique céleste, 1798 to 1825, the median ellipticities inferred from the available measures, 1 through 112 and 1 335.578, did end up favouring Newton. If the above were the entire story, I suspect you would take away the idea that the value of measurement lies in checking theories we already have at hand. It is true that this is one job of measurement, but it doesn't begin to exhaust its value to scientific knowledge.
The fact that hypothesis testing still dominates our ideas of measurement is an artifact of the armchair perspective favoured by philosophers and theoreticians, a perspective that focuses on relationships of inductive support and deductive entailment between unchanging theories and equally static bodies of evidence. Real theories and measures are living, historical entities. We can grasp the true value of measurement only by thinking of its dynamic role in advancing theoretical knowledge over time. Earlier, you may have noticed that the measurements that eventually favoured Newton's theory of universal gravitation, 1 divided by 312 and 1 divided by 335.78, differed from rival predictions, 1 divided by 578, and from Newton's own prediction, 1 divided by 230. That is not nearly as strange as it sounds, and doesn't conflict with these measurements supporting Newton's theory. The theory of Earth's shape based on Newton's law of gravity evolved from 1687 to 1798. While Newton's prediction applied only to uniformly dense bodies, Earth's internal density actually varies. The planet's core, for example, is denser than the crust. Laplace and other theoreticians did not have any decisive evidence for that idea previously. At the time, all they saw were discrepancies between Newton's prediction and their initial measurements. But rather than give up on Newton's law of gravitation, they went back to the drawing board to explain the physical sources behind these discrepancies. Laplace's explanation, radially increasing density inside Earth, was soon corroborated independently by its effects on other phenomena, like the changes to the orientation of Earth's axis and the surprisingly small deflection of gravity next to mountains or heavy test masses in the laboratory. Reflect on how remarkable this is. For the first time in human memory, we gained quantitative access to Earth's internal structure, and it came by explaining a discrepancy between a prediction and a quantitative measurement. The misalignment between topographic and gravitational bumps gave the first hints of Earth's internal dynamics. Deeper insights would follow. As measurements of Earth's ellipticity became ever more precise, new numerical discrepancies emerged, prompting new theories and discoveries. When writing, Laplace had access to only 6 measurements of Earth's curvature along specific meridian sections, many seriously flawed, and 15 measurements of its surface gravity at different latitudes. Selander and Struve's measurement of the distance between the Black Sea and Arctic Sea was one small part in extending the scope and precision of these measurements throughout the 1800s. By the dawn of the 20th century, Robert Friedrich Helmut could draw from more than 1,600 measurements of surface gravity, and measurements of surface curvature covered almost the entirety of the United States, India, Great Britain, and Europe, comprising several meridians in each case. While Laplace's data was collected by individuals using their own country's standards of length and time, late 19th century data rested on an international system of intercalibrated units. More data, better units, and better instruments soon showed Earth's gravitational field to have thousands of bumps of varying sizes, shapes, and locations. The gravitational sources of each of these bumps told us something about Earth's geology. The frequent misalignment between topographic and gravitational bumps provided the first key hints of Earth's internal dynamics.
As many would realise, Earth's crust can sink or rebound via a process dubbed isostasy. Isostasy, in turn, paved the way towards the discovery of plate tectonics in the 20th century. There are several other examples where efforts to make measurements of Earth's shape led to new, independently corroborated discoveries. Such efforts continue today, as satellite data and gravity measurements on the ground reveal fine details in Earth's gravitational field. The ellipsoid of Newton and Laplace is now mostly substituted by the geoid, a more complicated, bumpy equilibrium surface that roughly coincides with mean sea level. Our model of the geoid frequently shrinks or grows by a few centimetres, either because we build better instruments, run more calculations, or Earth literally changes. The best means for learning about the causes of such deformation, whether plate tectonics, seismic activity, or the melting of the Arctic ice sheets, continues to be minute discrepancies between predictions and measurements. Measuring Earth's shape might have once mattered to prove Newton right. The actual success of that effort, however, can be understood only if we pay attention to the myriad precise quantitative lessons it revealed about the makeup and dynamics of our planet. These might be new local insights about the composition of a mountain. They might be revisions to theory, as was the case when Laplace and his contemporaries extended Newtonian gravitational mechanics to account for the effects of Earth's density. Or they might be entirely new theories, as was the case when later scientists stumbled upon the theories of isostasy or plate tectonics.
Often the study of discrepancies in geodetic measurements spiraled off into entirely new disciplines. Earth's gravity is studied by geodesists, its internal structure is studied by seismologists, and plate tectonics is studied by geodynamicists. In some sense, much of modern geophysics is the sophisticated study of what once were systematic errors in geodetic measurements. So why does measurement matter? Why does science refuse to dispense with it, contrary to the initial hesitation of Aristotle, Galileo, or Descartes? Because it makes our collective investigations into the workings of the world more fruitful. When Selander set out to measure Earth's shape, along a line more than 2,800 kilometres in length, he was part of a long-term progressive research programme that would span centuries. One measurement leads to another, gradually forcing us to rethink our conceptions of what it is that we are measuring in the process. This insight into the intellectual purpose of measurement should also be a cautionary tale. Very often, we use measurement as a means for bestowing authority to our preconceptions. When we attempt to measure, say, human intelligence or economic performance, it is all too easy to think we are replacing vague ideas with mathematically precise facts. In many cases, there are plenty of incentives to accept such thoughts at face value. We need to resist them, as they display a deep confusion about the nature of measurement. Rather than a shortcut to the truth, measurement is a tool for learning, repeatedly, about the shortcomings of our ideas.